this one. Right. How is everyone? Good? Screen 2 share. Screen 2 share. Right. Let's see if this pops up correctly. 1 and 2. Good. Right. Hide that. That's the participants. Got 5 minutes left. Okay. What's that? Seems to be finished to me. Just get rid of that thing. Go away, go away. Just in case. Go away. Right, clear all on that. Right, so I don't know if any of you noticed, Virgin Media had some outages yesterday, so I'm hoping that the stream will be okay, but if I drop out, send me an email or a ping through Skype, and I should realise if I haven't already, but we might, well, I might drop out, I don't know, depending on whether Virgin Media have fixed their issues. Right, okay, let's get started then. So, quick recap of last lecture. We were talking about dynamic logic. We said in comparison to static logic, which always has a low impedance path from the output to VDD or ground, dynamic logic, on the other hand, stores the signal on a parasitic capacitance, right? This is the key, this is the biggest distinguishing feature of dynamic logic, right? So we saw how dynamic logic is manufactured with our pre-charge transistor. I will just switch this to the laser pointer. With our pre-charge transistor and our evaluate transistor, and then our pull-down network to implement the logic functionality. And we saw that our capacitor will charge up, and then in the pre-charge phase, and then discharge in the evaluate phase if the pull-down network provides a path to ground. Okay. We saw how the low to high time is 0, due to the fact that our input always starts off high, whereas our high to low time is our key critical path. It's the propagation delay of our gate, and it's what we need to design for. But because this is all dealing with NMOSes, and NMOSes tend to be... Oh, am I muted? My microphone is on. That one's on. Interesting. Yeah, that's odd. Can you hear me now? Can you hear me now? No? Something's gone wrong. Okay, just a sec. Sound settings. Oh, for God's sake. Can you hear me now? No, probably not. Can you hear me now? God's sake. There. Right. What's happened? For God's sake. I will just leave session. Poor. Others couldn't hear me. It's an exit. Right. Leave session. Poor. Others couldn't hear me. Right. Close that. 14. Join session. Close. Join session. Right. Can you hear me? Can you lot hear me as well? Brilliant. Right. Okay. That's good. Yeah. Sorry about that. My system decided to change the default microphone for some stupid reason. So yeah. Right. Attempt number 2. So I was just going over what we saw last lecture, but I will skip ahead. Basically, we just saw that dynamic logic has this capacitor which we charge up, and then we discharge if we need to. It's got 0 low to high time, and then high to low time dependent just on these NMOS transistors, no extra parasitic capacitances from a pull-up network. We saw that if we have a glitch in our output, our dynamic gate will fail, so we can't have glitching. And we saw that the power is higher than complementary CMOS and is purely dependent on the number of zeros in our truth table. Right? We saw that there is some charge leakage. So this was the first issue with dynamic design. We've got charge leakage because our transistors are not completely off. They're only like a 10 to the 5 difference between on and off. And then with low VT transistors, that gets even worse. And then we also have leakages down through other parts of the transistor. And so what we saw is that there is a maximum time period between pre-charge phases based on that leakage current and the amount of charge that can be stored in this capacitor. And because there is a maximum time between pre-charge phases, there is a minimum clock rate. Right, and then the point to which it can discharge is defined by the margin point, which is VTN, the threshold of an NMOS transistor, presuming that the output is connected to a set of dynamic logic as well. We saw how we can use a keeper transistor to deal with charge leakage, where we just introduce a level restoring inverter, and then we use that level restoring inverter to drive a keeper transistor, which pulls the output node, well, the internal output node high. But then we saw that our logic becomes ratioed. This pull down network needs to be able to overpower that keeper transistor. Obviously, we've got the electron hole mobility difference on our side, but depending on how strong that electron hole mobility difference is and the resistance of this network, you may need to size up your pull down network, right? And so we saw a few examples here. So we said if A and B have a size of 1 and the keeper has a size of 2, then it can't overpower it, with the keeper being a size of 1 and then A and B either being size 2 or size 1. It will overpower it, but the time it takes to do so will be longer or shorter. And it's the same as with pass transistor logic. So, getting on to today's lecture, the next issue we need to deal with is something called charge sharing. So let's change back to a pen. Right, so imagine that initially both this transistor and this transistor are turned off, and we pre-charged just CL up to VDD, right? Then our clock goes high, meaning this one turns off. Our clock goes high, meaning this one turns on. And our A goes high, meaning this one turns on. This one is still off, by the way. We'll see that the charge, which is initially stored purely in CL, will then be redistributed into CA as well as CL, right? So it will balance out the voltage between these two. So because this is because this is now connected, we've got two different potentials here and here, so a current will flow through until the potential at this point and this point equalize, okay? So originally we would have had the charge here, Q, L, equals CL VDD. We charged up to VDD, so the voltage over the capacitor is VDD, and the capacitance, it's just this one capacitor, CL. So that was the charge before. After, we've got QL plus QA, so the charge in L and the charge in A, which must be equal to QL, but that is equal to CL VL, so that's the voltage across L times the capacitance of L, plus the capacitance of A times the voltage across A. After some time, so t tends to infinity, obviously it doesn't need to get all the way there, it can just be some largish amount of time, VA becomes VL, they equalize, and therefore we see that QL VDD equals QL CL plus equals CLV out plus CAV out. and therefore we can just rearrange this slightly. So VDD, sorry, that's supposed to say CL, sorry, CLVD, so, and then CL over CL plus CA equals V out. Yeah, sorry, those Q's were supposed to be C's, right? So we get this equation, right? Originally, we just had the charge stored in CL, but now it's stored in CA plus CL, and so the charge is going to be redistributed. If we've got enough capacitance down here to drop V out to be less than Vm, which is Vtn, right? The midpoint, which is our threshold n, then our circuit will malfunction. So we need to make sure there's not too much capacitance which is connected down here, which it could then discharge into, right? Which it can charge share between, right? So if we imagine CA equals 10 picofarads and CL equals 1 picofarad, if this were the case, then it's quite clear that we're going to drop very far below VTN and will malfunction. If it were the other way round, so CL was 10 picofarads and CA was 1 picofarad, then it will just be a minor drop, right? So question is, how do we stop this if we have got a large enough capacitance here that it becomes a problem? We do the same thing as we did with the output node when it was just leaking, except instead of having a keeper transistor, which when we're evaluating it'll still be pulling it up, instead we just pre-charge this parasitic capacitance, CA, up to VDD when the clock is high through this pull-up transistor, and then that transistor turns off when the clock goes high, and then this node can be discharged along with the output if need be, right? So what we're doing is we're just pre-charging CA so that, just as before, we've got QL plus QA afterwards, or how, no, better way to explain this. So afterwards we've got CL, CA, CL, VL plus CA, VA equals Q, but Q from before is now VDD CL plus VDD CA, right? We've added on this VDD CA component compared to here by pre-charging this parasitic capacitance. Therefore, when we connect the A transistor, we've got that Q is going to be CL, CA, VA plus CL, VL plus CA, VA, which obviously that is going to imply that these two are going to stay at VDD unless B turns on, in which case obviously they'll all discharge down to ground because all that charge will go down that way. Okay? So that's charge redistribution. Need to be careful of how much parasitic capacitance you've got. Just click that one, click that one, click that one. Right. After that, so we've seen that we can design a single dynamic gate on its own to work properly, right? What happens when we start to cascade them? Do they just work perfectly like CMOS gates do, or is there maybe some issues with it? So we've got two dynamic gates here. Both of these are inverters. So that's the equivalent of this. So what we would expect is that would go to that, which would go to that. Rising edge causes falling edge causes a rising edge, right? So we see our input over here rises. Out 1, so obviously before the clock is high and that pre-charges this node to VDD, right? Then our input goes high and our clock goes high, meaning our evaluate transistor turns on and our input transistor is on, and so our output discharges down to ground. Out 1 specifically, right? What's happening over here? Well, this transistor starts off on and transitions to off, right? Because its input starts off at VDD and transitions to ground. So here is, where's VTN going? So here's VTN on out 1. Once it gets below that point, it's off. Above that point, it's on. And so however, the clock has already transitioned high. So this one has turned on before this one turns off, but only a short amount of time beforehand. And so what we see is that our output transistor starts discharging when the clock goes high. Our out 1 starts discharging when the clock goes high, as does our out 2. When out 1 gets down to VTN, out 2 then stops discharging at that point, and so we lose a particular voltage, delta V, right? Depending on how long it takes out 1 to discharge down to VTN. Obviously, as it gets closer to VTN, this transistor gradually shuts off. It's not a binary switch, as we saw, but for the most part of it, we've got constant current going through here, and it's only near this end bits that it really starts to level off. Okay, so we need to consider, well, depending on where our clock is, how long it takes to discharge this node, we might end up with this going all the way down to VTN, going below VTN, and hence resulting in a 0 at the output, and have a functional problem. So we need to consider how much this is, right? In order to avoid this delta V drop, we're only allowed a single 0 to 1 transition at the input, right? We're not allowed to discharge this, we're only allowed to charge it. Not allowed, right? So how do we deal with that? We just add an inverter in there. So there's two possibilities for this node. Because it's been pre-charged, it'll start off at a 1, and then it'll either stay at a 1 or go down to a 0. However, unlike in our previous circuit, where we've connected it directly up to the next signal, we've got an inverter here. So the output of the inverter, because the input started at 1, the output will start at 0, and then it will either stay at 0 or transition to a 1. Notice how we've got a 0 to 1 transition here, rather than the 1 to 0 transition that we started off with. Okay? In this case, because our out 1 starts at 0, we're not going to have that delta V problem. So we're going to see our clock will go high. Our in 1, we'll put that one high here. So there's in 1, there's clock. Right. Out 1, out, sorry. Let's get rid of that one. So I'll call this O1 bar. So O1 bar will start off high, and then when the clock goes high, it'll discharge. Out 1, just here, will start off low, and then it'll charge up. And then if we look at O2 bar, which will be just here, we'll see that because it starts off, it'll stay high, and it's, even though the clock's high, sorry about the doorbell, someone else will get that, it'll stay high until O1 starts to discharge, charges up, at which it'll start to discharge. Okay, so we won't get any glitching, right? If O1 didn't go high and it stayed low, it would stay up here. We wouldn't drop the delta V, right? Why do we call this domino, by the way? Because they fall like dominoes. All of them have this note here, start high, 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 and high. And then this one drops, and then that one drops, and then that one drops, and then that one drops, right? Domino logic, because they fall over sequentially, okay? There are other ways of dealing with this issue. For example, you can have logic where you have a pull-down network as normal for our first stage, right? And then on the next stage, you have a pre-discharge transistor, and you have a pull-up network with the evaluate transistor at the top. And then on the next stage, you have your pre-charge transistor at the top, and you have a pull-down network with your evaluate transistor, and then back to for some reason this doesn't want to disappear. Okay, it won't disappear. You have your, no, that's why I drew this wrong. There we go. Thought this was a bit wrong. Then that one goes into there, and then again we have our pull up network, our pre-discharge transistor, and our evaluate transistor. So you can do that where you have alternating pull down and pull up networks. This is much higher area than the domino logic scheme, because in a domino logic scheme all you add is one inverter, as opposed to adding all the extra sizing required for a pull-up network, because our pull-up network will need to be bigger than our pull-down network due to the difference in electron hole mobility. So it's greater area and greater power, but because we don't have an extra stage of logic just here, it can be a bit faster again, right? So you can do this, right? So in conclusion, like now we've seen that there the different types of style, where we've got our complementary static styles, so that's the pass transistor and the complementary CMOS. We've got things like complementary pass logic, and then we've got dynamic domino logic, right? How do we choose a logic style for our design? Well, at the end of the day, it comes down to what we're trying to optimize for. If all we care about is delay, we'll go for a dynamic style like domino logic, because it's always faster, because we've got less parasitic capacitances, because we've got a certain amount of sequential aspect to it, those sorts of things. It's a much faster type of logic. Conversely, if we're going for ease of use, we'll always go for complementary static, except if we've got specific types of circuits, like sometimes adders and XORs are easier to do with either pass transistor or complementary pass logic, right? And then you've got certain particular types of design, like FPGAs and that, which are better off with complementary pass logic or a pass transistor logic, purely because it allows them to be more regular and it allows the routing aspect of it to be done easier. And same thing with semi-custom ASICs. They're better off with either a NAND architecture or complementary pass logic, where you can just reconfigure the routing and leave the logic cells as they are, right? Generally, in industry, the current trend is towards more CMOS usage. In the past, dynamic logic used to be key for microprocessors, and you had pass transistor logic and all sorts for discrete logic and sensors and things like that. Current trend is to just use CMOS because it's so much easier to develop when you've got a chip with 5 billion transistors on it, trying to fix all the parasitic capacitances and determine the timing issues and glitches with domino logic is really quite difficult. So we get more and more CMOS logic on our chip, and we only ever consider things like domino logic for the key critical paths, the ones that really affect the performance of our chip. And also, all the tools generally tend to be better at doing CMOS logic because it's just easier for the tools to work with. It's more robust, the tools support it better, and it's also a bit happier to deal with voltage scaling. CMOS is fine with voltage scaling. As you change the voltage in other types of logic, it can mess around with it a bit too much. So you need to be very careful of voltage scaling with other techniques. So we get more and more CMOS logic. And that is the end of the dynamic lecture. So there should be an annotated version of this already uploaded to Blackboard. I will just check that myself because I don't trust myself to be correct here. Lectures. Yes, it is already uploaded. Good. Right. So next lecture will be the lecture on timing. So this is sort of going back towards the sequential side of things. So yeah, next lecture is system level timing. And we'll be looking at static storage and dynamic storage. So knowing what dynamic logic is will help in the understanding of dynamic storage. And then the static storage is what we saw with our sequential lectures. So that will be next lecture, which will be on Tuesday at on Friday the 1st of May at 11 o'clock GMT. So you should have seen the email I sent out with the calendar invites in it. So that should give you the value in your time zone. Okay, I will wrap it up for there for today then. Are there any questions? Email from, okay, I will quickly have a look at that. Give me 1 second. I can't do that. Just open a new copy of Outlook, that'll do. Right. Email. Okay, question from Joydeep about a circuit he found. Quite interesting that the PMOS transistors are connected up to VDD. That's not something that usually happens. What is this circuit doing? So we've got an MMOS, or no, are these MMOSes or PMOS? I'm not sure what those are. They're all NMOS transistors. Okay, so we've got a VDD with the inputs of the NMOSes connected up to it. So those are, so they're acting as pull-up transistors, weak pull-up transistors, I presume. Yeah, give me a while to analyze that and I'll reply to it. Yeah, so this is a rather interesting circuit. I'm not sure. Yeah, no, give me a while to analyze that one. It's not a trivial circuit to analyze. Yes, they're almost acting like pull-up resistors, but not quite. Um, so yeah, give me a while to analyze that one, and I'll get back to you on that. Um, any other questions? No. Okay, I'll wrap it up for today then. Um, yeah, have a good week, everyone. Oh yeah, and I will upload the test for dynamic very shortly. I believe the test for sequential logic is still open. Please do give that one a try if you have the time to do so. But yeah, I'll upload the test for dynamic logic shortly. Okay, bye.